So hello, I'd like to welcome you all to Physics 2, now with internet. Um, so yeah, a bunch of you have had me before. There's actually there's a bunch of people who haven't had me before, which I wasn't expecting. Um, those who had me before, you know the deal, but I'm kind of going to go through a quick version of everything for everyone. Um, yeah, this lecture, Monday, Wednesday, Friday, 3 to 4. I'll traditionally only lecture Monday and Wednesday. Friday will be for example problems. I'll talk about that at the end of the week. I am your instructor, Dr. Lars Schweidenbach. For those of you who don't know me from before, two things. One is I do have a speech impediment. I can't say my own first name correctly. So say my name how it's spelled, not how I say it. Second of all, my last name is really goddamn long and scary. Nobody uses it. Just call me Lowe's. That's fine. There's my email. There's my Zoom room, which those of you in the Zoom room obviously found. And there's the YouTube video, which I guess you guys, those of you who are watching it through YouTube, have already found. I'm going to kind of do a little bit of syllabus stuff today. I'm going to do a little fast because a good number of you have had me before, and I kind of doing the same thing for Physics 2. I did for Physics 1. But I will do a quick version of it. But yeah, that's me. Feel free to interrupt me whenever you need to. If you're doing this synchronous, it means you want to be able to have an interactive class. Whenever you want to ask a question, you can send it in the chat. I have that open on my second monitor. Or if you want, you can just unmute yourself and talk. I have it set that I can't see all of your videos just because there's only so many things I can have on the screen at once. So if you try to like wave to get my attention, I won't notice. But feel free to unmute yourself, interrupt me, and just say, you know, what the hell are you talking about? Slow down. What the hell? I'm confused. Interrupt me as needed. I will happily help. So in general, it is all online. I've said this before in emails, but so I'm saying it again for no reason apparently. Lectures happen now at 3 o'clock, and you can either go to the live stream or watch the VOD. I actually don't care which. I feel like I should care more than I do, but as long as you're getting the information, I'm happy. I personally think that watching the live stream would be probably better because that way if you have questions, you can ask them as I go. But if you can't, the videos are fine. And if you have questions with the videos, you can just email me and I'll answer them. This isn't the world's easiest class. Sometimes you will need help. That is fine. I am doing office hours as always. I have a good amount of office hours. Here it is listed, but if that's what I didn't open. I had to reopen everything because the computer crashing, and I forgot to reopen the Vanco Hall page. Yeah, I have lots of office hours, the majority of which I put on Wednesday. That is because of homework is due Wednesday. And I also have some Thursday that surround when labs are due, which I'll talk about in a second. Meanwhile, let me open up the Vanco Hall page real fast. Sorry. But seriously, my computer at 2:50 is deciding to crash really kind of just put me in a sense of panic. So there's my schedule in picture form. So yeah, my office hours Monday, Wednesday, Friday earlier in the day, but also a bunch later in the day. So you need help, come. If you can't make them and you want help, email me. I'll also work by appointment. Okay. Grading setup is I am grading 25% homework, 25, did not do that yet. 25% homework, 25% labs, 50% exams. I dropped the lowest homework, I dropped the lowest lab. The exam breakdown is the same as Physics 1 for all of you who have had me. It's exam 1 is 25, exam 2 is 25, final exam is 50. Once again, those who had me before, if you had me last semester, it's going to be basically the same as the second half of last semester. If you had me before last semester, it's the same thing, but online. And those of you who took Physics 1 with someone else, that's the setup. I don't know what I'm saying. Like before, homework and labs, all half your grade. If you want to do well in this class, just keep your homework scores and lab scores up. There's really no excuse to have low scores on them, because if you need help, you can get it. If you're getting low homework or low labs, come to office hours. Come get help, and I will help. I think you pay enough to go to college that charging you extra is just a horrible thing to do. I don't think textbooks should cost money, and so I do not require a textbook. If you want a textbook, I can recommend one. That's a recommendation right here. Survey and Rule, College Physics 10. But honestly, don't. Textbooks are expensive. I will give you everything you need without it. As I said before, homework is online. The homework will be right on Vanco Hall down in the homework section. Each homework is due Wednesday night at 11 p.m. starting next week. Traditionally, I will cover a chapter each week, and the homework is due the following week. How it's going to work, same way as last time. Actually, I guess there's a few of you who haven't had me before. Now that I look at who's in here. You have 4 attempts each problem. When you log into the homework, since there's some of you who haven't had me before, I will cover this in more detail than I planned. When you log into the homework, there will be 10 pages of problems. It really is what I consider 10 problems. Some of them have A, B, C, D parts, so it looks like more. And what it is each one of the boxes is a point. And when you go in, you have 4 attempts. You can put in your answer, hit check, and if it's correct, it'll give you the points. If it's not correct, it won't. And you don't lose anything for incorrect answers until the 4th one. Each individual problem, you have 4 attempts. When you get it correct, either a meme or a GIF will show up. If you get it wrong, you get this yellow box saying to try again. So what I recommend is try to do the homework. If you can't do a problem, go and one of my office hours and get help. It'll let you change them however you want until you hit submit. You can leave it and go back as you want. So, I mean, I could just take this, move away from that website, and it's fine. I can go finish it later. Make sure when you put your answers, you include your units. I'm not going to go heavy about units in this class. I figure even if you took Physics 1 with someone else, you talked about units enough, then it will require units. If you ever get a GIF or a meme, but it says the answer is wrong, that means your number is correct, your units are wrong. Like always, if you have any issues with the homework, just email me. If you think Vanco Hall messed up, let me know. If you need an extension on the homework, let me know. And I would try. It says that many of these are old test problems. That's not true for this class. This is actually only my 2nd time teaching Physics 2, so I don't have much of a test bank to work from. And I purposely didn't put the test bank into the problems because you're going to get last semester's exam is review. But I will try moving. They are very similar to exam problems. The exams are the only thing I do synchronous. The exams are going to happen on 2 different Fridays, plus whatever the final is, at 3 p.m. The exam is like the class you can do synchronous or asynchronous. You can either be here live for the lecture or you can watch the videos. But the exams have set time. They're going to start at 3 o'clock. What's going to happen is on Vanco Hall, a PDF will show up and a spot to upload. And what you do is you either print it and do it on paper, or why bother printing? Just like keep it on the screen and just do it on paper. Once you do it, take pictures of it, upload the pictures, and I'll grade off that. Those are a set time to just kind of lessen cheating, but it will only be from 3 until 4:05. Normally, I only give 50 minutes for exams. I'm giving an extra 15 minutes to have time to upload. I'll talk about this a lot more as we get forward, but just know those 2 days at those times, you're going to need to be online. Any questions so far? I admit I'm going a little fast. but it's syllabus bullshit. And a good portion of you have heard this exact same thing before from me. You good? Okay. Oh yeah. So yeah, I think as I said before, questions in chat works or just out loud, either one. The exams will be open notes, mostly because I have no control over that, but you must do the exams on your own. You cannot work together. I'm planning on making parts randomized to lessen that. Those of you who had me last semester, you saw I randomized the numbers. I'm considering actually randomizing exam problems and writing more exam problems. I haven't quite figured out what I'm doing yet for the exams. But that's the idea. The labs are also online. Now, online labs are borderline pointless, but I'm still doing them because I have to. What it's going to be is labs are going to be based around 3 p.m. on Thursday, which is when our lab time would have normally been. What's going to happen is every week at 3 p.m., 3 different things will show up. You will get a PowerPoint explaining the lab, a link to a video for you to watch the lab, and the actual assignment itself. I recommend you read through the PDF, then you watch the video, and then you open the document. And the first one's going to show up this Thursday at 3, and you have to do it before next Thursday at 3. And every Thursday at 3, one will close, another will open. Of note, that surrounds my office hours. I have office hours on Thursday from 2 to 3:30. So if you want to wait to the last minute and need help, I will be on office hours. If you want to do it right when it comes out, I'll be on office hours. And yeah, you'll go through and just fill in all the stuff. The procedure will tell you exactly what you need to do. The first lab's a little different than most labs, so it's kind of weird to look at. Sometimes you have to upload things, and there'll usually be post-lab questions and the conclusion. But every Thursday at 3 p.m. Basically, just fill out everything it asks for. The post-lab questions, you can either just type a number in a box or do it on paper or take a picture of your work and upload it. I recommend the latter. I grade heavily on partial credit. And if you have all your work correct but make a math mistake, you can still get most of the points as long as I can see the work. So when you do the post-lab questions, you should really upload that. Also, I always ask for conclusion. Conclusion asks for sources of error. Take a look and see what sources of error you have. For those of you in Zoom, which is everyone who's listening right now, but I guess there's people listening in the future. I don't care if you have your camera on or not. I literally have it that I can't see your camera because once again, it just takes up too much of the screen. Like if I go to it, it's just a whole thing of stuff getting in the way. But I do ask you mute yourself unless you're asking a question, which you all did. However, if you have a question, feel free to, whenever you want, unmute yourself and ask the question. I mean, if you really want, you can sit in class unmuted, but there's the chance that like someone walks through the background yelling at you is way too high and happens from time to time. But feel free to unmute yourself whenever you need to ask a question. Or you can post questions in the chat, as I have seen comments in the chat already. I have it open on my second monitor, and I do keep track of them. I do like the class to be interactive, which is hard online. I'm going to do my best. Like, I like to teach with demos and running around a room, and I like sit stuck in a chair. It's pretty fucking miserable in my mind. I actually kind of hate this. The world sucks. But I will be doing my best to keep it interactive. I'll be doing a lot with the PowerPoint. There's a lot of the actual Zoom video will show me doing things. So good if I have that open also, because I have physical demos for me to like move videos of other demos, but I'll do my best. Everything is posted on Vanco Hall. The YouTube links, these videos, do what you need to do. If I go too fast, let me know. I use the Vanco Hall gradebook. Yeah, that's all the syllabus stuff I'm going to say. As I said, I did the syllabus stuff kind of quick, but The majority of you have had me before. And those of you who haven't, hopefully I covered enough. If you're confused, email me. I'll go in more detail. We good with syllabus stuff? Let's talk physics then. So you are now in physics 2. You have made your way through physics 1, which was all what is called kinematics. How things move, flying through the air, you push on stuff, energy, work, a little bit of thermodynamics in there at the end too. But that doesn't really explain everything about the world. How it doesn't explain the biggest way we interact the world, looking at things in optics. We never touched on electricity and magnetism. And we didn't get into more modern discoveries of physics. See, physics 1 is it's not even half the story. It's like a quarter of the story, but it didn't get very far into explaining things. Now that we're in physics 2, we're going to talk about things that are either really small or no, we're just going to talk about really small. We're going to talk about what happens on a small scale where things get crazy. We're going to start with electricity, move to magnetism. From magnetism, go into optics. And after we do optics, we're going to get into modern physics, which shit gets weird. That's the shortest version of optics, of modern physics. Yeah, shit gets weird. But that's what we're going to be doing here. Electricity and magnetism to optics, which are interestingly related. They actually flow from one to the other. And then modern physics. Now, before we get started, I want to do a very, very, very quick review of stuff from Physics 1. And that's just vector algebra. Vectors haven't gone away. And you might remember in Chapter 4 in Physics 1, dealing with forces and being, where is that back? Sorry. You may remember in Chapter 1, dealing with forces and being like, okay, I have two vectors. One pointing this way, one pointing that way. I have to add, no, that one doesn't show up well against my face. Let's grab a different color. One going that way. Okay, I have to add them. Let's deal with the vector addition. It was a thing we had to do a lot in Physics 1. And I'm here to tell you now, no matter what you wish was true, that isn't stopping. We're going to be dealing with these vector addition a lot again. So I want to make sure you remember it, which is why I'm going to do a quick review. Anytime you have a vector, and let me quickly anytime you have a vector pointing along any direction, you have to be able to split it into components. You see, if I try to do any physics on that blue vector on the xy plane like I have it, it's going to be really, 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 really complicated. And what we do to make life easier, actually I want to make this bigger for a second, is we're going to split it into components. How far is it along x? How far is it along y? And taking a vector like this one and turning it into two other vectors, one this way, one that way. That's done to simplify the math. And so what's going to happen is you have to be able to find the components, the x and y components of any vector, which is based off SOHCAHTOA. As long as your angle is measured from the horizontal, which it usually is, but if your angle is measured from the horizontal, the y component of any vector is the magnitude of the vector times the sine of the angle. The x component of your vector is the magnitude of the vector times the cosine of the angle. This should be familiar. I mean, we did this a lot in Physics 1. We're going to need it a lot in Physics 2, starting even with the chapter that we're about to get into. Now, if you have your x and y component, so if you have this and this, and you want to go back to that guy, what you do is use Pythagorean theorem. The x component squared plus the y component squared, square root of, is the magnitude. And we can also use that the inverse tangent of y over x is the angle. Is this familiar to everyone? So anyone this doesn't seem familiar? Okay. Once again, you've seen this before. If you have to add vectors, anytime you have to add vectors, break them into components. If I have to add a vector A plus a vector B like this, if I want to add that, what I do is I'll find the X component of each vector and add those. Find the Y component of each vector and add those. Or I can say the X component is for A is A cosine theta A. The X component of B is B cosine theta B. For Y, it'll be A sine theta A, B sine theta B. And then you can add up your X's, add up your Y's. If you want to find magnitude and direction, Pythagorean theorem and inverse tangent. Okay?
Mm-hmm.
Okay, that was everything you needed to remember from Physics 1 right now. There's more stuff that'll come from Physics 1, but none detail. But I actually am gonna, we're halfway into class. I'm gonna start the actual physics. I did that fast. I know I did that fast. I'm gonna try to slow down here. But that was all stuff that syllabus is boring and the rest of the stuff you've seen before. And I numbered the chapter starting with chapter 20, just because if you had me for physics, so you could separate out the two classes, that chapters 1 through 12 of physics, 1, 20 to 32 is physics 2. But we're going to start jumping right into electricity and electric forces and electric fields. Now, another thing from chapter 1, right? Newton's second law, F equals ma. When we talked about Newton's second law in physics 1, what we said is that forces are a vector that can cause acceleration. When you push on something, you can find out how fast it accelerates and in what direction it accelerates if you know with what direction, with what force you push on it, and the mass of the object. And we talked about a lot of forces. There was the normal force, there was tension, there was the force of gravity. But we only talked about contact forces. And I don't remember this back in chapter 4, but I said there was two types of forces, contact and non-contact forces. But you can sometimes create some other forces with electricity. That if you take a charged particle, you can apply forces to it and make it move. And so what we're going to do is we're going to talk about the forces on electric charges and how they're created and how they act. Thing is, if I'm going to talk about the forces on electric charges, let's start with what the hell is an electric charge? So, around 700 BC or somewhere between, 700 BC, ancient Greeks learned that things had charges. They weren't quite sure what it was, but they realized that sometimes you could rub some things together and they'd stick together, or rub one thing, rub something else, and they push apart from each other. That was real. The whole idea: take a balloon, rub it against your shirt, stick to something. They're not balloons, but they worked that out. You could do that, and they're like, there's something going on here. A lot of people thought it was like spirits holding stuff together and weird stuff like that. But around 1750, Franklin, as in Benjamin Franklin, he realized that there was two types of charges, and he named them the positive charge and the negative charge. Now, fun fact, this can come back later. He arbitrarily named something positive, something else negative. If he had flipped them, if he had called what he called positive negative and what we called negative positive, all of the math would be 20 times easier. But he just guessed which one was which and kind of got it wrong, but we stuck to it because yay. But he said there's two types of charges, the positive charge and the negative charge. Now, positive charge is just, the charge is positive. Positive charge is made up by protons, or at least too many protons. Every atom made up of protons, neutrons, electrons. I assume you know that. I'm not really going into that in detail. And each proton has a positive charge of 1.6 times 10 to the negative 19 coulombs. There you go. The unit for charge is the coulomb, or capital C. You also note I said this Q sub P. The symbol for charge is a Q. I have no idea why we use Q for charge. You would think charge should be C. It would make sense, but it's not. It's Q. Sorry. Negative charge, on the other hand, is moved by electrons, where each electron has a charge of negative 1.6 times 10 to the negative 19 coulombs. And what they found is that if a charged thing is when they have an imbalance of electrons and protons. You see, an atom in general should have the same number of both. If you have a hydrogen atom, it should have 1 electron, 1 proton. If you have an oxygen atom, it should have 8 protons and 8 electrons. And if you add up the total charge, it means adding up the charge of the protons plus the charge of the electrons. Most things should have a charge of 0. Because its total charge would just be, adding 1.6 times 10 negative 19, then adding negative 1.6 times 10 negative 19. By default, most atoms have no charge. But here's the thing. You can remove electrons from atoms. You can also add electrons from charges. This is covered a lot more in a chemistry class. I'm going to hint on it some, and I'll talk about it more when I get into modern physics. But for now, just know you can pull off electrons. You can mechanically do it. I'll have a video in a second where I mechanically did it. But you can remove electrons from something, or you can add electrons to something. You can't actually change protons, or you can, but when you're changing protons, you're dealing with radiation and it's explosive, changing protons. Let's go with that. But if you add electrons to something, it will then have more electrons than protons. It'll be negatively charged. Likewise, if you remove electrons from something, it'll have more protons than electrons. It'll be positively charged. And anytime something has a charge, it is because it either gained too many electrons or lost some electrons. Now, the reason this matters is things with charges will interact with each other. If you have an uncharged object and another uncharged object, it's just going to be like nothing. It's fine. But if you have two charged objects, they will react. They will apply forces. And it will be based off the law of charges. And what it is that like charges repel, unlike charges attract. Anytime you have two things with the same charge, they will push away from each other. If you have a positive and a positive, they will shoot apart. If you have a negative and a negative, they will shoot apart. But opposite charges will attract. And if you put a positively charged thing next to a negatively charged thing, they will suck together. That was my ring right into my knuckle. That hurt. Anyways, I'm good at my job. If you have opposite charged things, they will attract together. And they will either move directly together or directly apart. And they'll actually always go with the same magnitude of force for the two of them. Because it's going to be forces. That's what it is. Like charges have a force pushing out. Opposite have a force pushing in. And they'll follow all of Newton's laws. We can say F equals ma and get the acceleration. We can also say Newton's third law, that whatever the force on this guy is going to be the same in magnitude of the force of this guy, because for every opposite is an equal and opposite reaction. And this can actually be shown explicitly. So, some weird things. If you take a glass rod and rub it with silk, you will rip electrons off of it. And anytime you take a glass rod and rub it with silk, it'll become positively charged. Now, for the record, you cannot create or destroy matter. You're not making electrons just vanish in thin air. You're just removing them from the rod. What will happen is if you rub a glass rod with silk, the silk will become negatively charged. It'll take electrons away. But the glass rod will become positive. You can also, the stuff you can also do with rabbit. I gotta check what my video did. Likewise, if you take a rubber rod and rub it with silk, it'll deposit electrons. And when you rub a rubber rod, yeah, someone who can't say, oh, so that's the sentence I'm going with today. Yay! You will rip electrons off the silk and put them on the rod, giving it a negative charge. And we can use this to show what I was talking about with charges. This one. So here I go. I have a silk thing, and this is the rubber rod. And I'm rubbing my rubber rod with, and now by rubbing that, it now has a negative charge. I took another rubber rod and did the same. And as you can see, let me go back to that real fast. Well, I'm going back and forth. I'm not touching it when I'm doing this. I'm bringing it close, but I'm making it stop spinning one way and start spinning the other. That's this opposite charges, like charges thing, that I'm taking a negatively charged rod and bring it near another negatively charged rod. And by bringing the two negatively charged rods near each other, I'm applying a force. I'm causing it to accelerate by applying this force. That's all. This is this idea in general. Okay. Now this right here is my glass rod. When I take this glass rod, it's going to become positively charged. And so what's going to happen is it should attract the rubber rod. And if you can see, I got that to spin up. And here I got to slow down and spin up in the other direction. Apparently I wanted to give it more charge. And all that is the idea of this attractive force, that I can pull the glass rod and the rubber rod near each other because they have opposite charges. All I'm doing is moving electrons. Okay. Now when you talk about static shocks, like it's cold, you rub your feet on the ground, you touch a doorknob, like, shock. That's all it is. If you go and like rub up against something, what you might do is you might rip electrons off you or rip electrons off the ground, giving you a net charge. And so in the middle of the winter, when you, side note, charge travels better when it's dry. The reason you get zapped static charge more often in the winter than the summer is the air is drier. Because the way we heat houses normally removes moisture from the air, and the summers, especially here, can get kind of humid. But there's less water in the air when there's a few other reasons too, dealing with temperature and water that can stay in the air. But when it's cold, you're more likely to shock just because it can conduct electricity better. But if you rub two things together, or you know what? Give me a second. If I take this balloon and like rub it up against my shirt, what I'll do is I'll move electrons. And by moving electrons, I don't know what I have visible that I can stick this to. I can get it to, nope. It's sticking to my hand for a second. We can move electrons, and what happens is you can get it so that it has a set charge and attract to other pieces. That's what happens when you shock yourself, is you're moving some electrons and giving you a net charge. The reason you feel a zap when you touch someone else or something metal is what you're going to do is if you have extra electrons, you're going to get rid of them. Or maybe you have too many, or maybe you'd have not enough electrons. You're going to pull them back. The process of the electrons moving, that's the zap you feel when you shock yourself or shock someone else. That anytime you have friction, you can create a charged object. And things don't like being charged. And so, yeah, shocks are just you trying to uncharge yourself. This is why they make a big deal when you fill a gas tank, you never put in the bed of a truck. If you have it on the bed of a truck, it can cause some friction. It might build up a charge. When it's on the ground, if it's on the ground, I'm going to talk about grounded later on, but anything touching the earth will always have its net charge of 0. Because, well, the earth has a lot of electrons in it. And if something has too many or not enough and it touches the earth, it'll equalize out. And so when you fill a gas tank on the ground, it won't build up a charge. It won't be rubbing. In the back of a truck, it may build up a charge. And if you build up a charge, charges can cause shocks, little bolts of electricity. Little bolts of electricity can ignite things. It's kind of a big deal. Okay. Now, when dealing with charges, different materials will deal with charges differently. This is getting really far into chemistry, but I'm going to kind of gloss over the chemistry bit because chemistry sucks. But some materials, my mouse is not visible, which is annoying me. There we go. Some materials, the electrons can move freely. Anything that's normally a metal, it would be a conductor. In a metal, the electrons can move freely wherever they want throughout it. And so any material where the electrons can move freely will be a conductor. What that means is that, yeah, they I have a note here that I just laughed at. They can move, the electrons can go wherever they want. Anything that conducts electricity well, copper, aluminum, silver, gold, like things in electricity, like gold is one of the best conductors. That's why you sometimes get gold plated things for wiring. But most wiring is copper because it's cheaper. Conducts really well. This is things that conduct well, it's just because the electrons can move freely. Things that do not allow charge to flow are insulators. And those are things that the electrons cannot move. This balloon, I gave it a charge, right? By rubbing against my shirt. And I think I even have a better video of me doing the balloon thing, which I'll come back to in a second. Even it's picking up cat hair, that's what it's doing. Even though it's an insulator, I can still give it a charge. Insulators are if you give it a charge, it'll probably keep the charge and not want to change it. It'll be harder to put a charge in it, but yeah, won't really pass things through, but it'll keep whatever it has. Really, it's everything that isn't a metal for the most part. Ceramics, dry wood, plastics, and so on. There is the weird shit in between, semiconductors. Semiconductors kind of conduct and kind of don't, and they have a lot of stuff they can do, and that is honestly its own branch of study. Semiconductors is its own separate class. My PhD is in semiconductor physics, so I can explain it if you want, but that is that's a few steps beyond where we're going. There's also called superconductors. Superconductors are things that perfectly conduct. They yeah, can move really freely. Only works at really low temperatures. I'm talking like single-digit Kelvin. I had a superconducting magnet for my research. It had to be at 4 degrees Kelvin or it didn't work. That's a little more crazy. Now, if you want to move charge, you can move charge a few different ways. One of the easiest way is charging by conduction. What happens is if you take something and charge it, and it works better if it's one of the two things is a conductor, but it doesn't have to be. But if you take something and give it a good charge, and you touch it against something else, what will happen is once they touch is the charge will balance. If you look at this diagram on the right, I have a rubber rod that's negatively charged and some sort of sphere that is uniformly charged. This rubber rod has way too many electrons. When I touch it to the piece of metal, it will try to get rid of more of its extra electrons, but it'll balance out. It won't get rid of all of them. It'll just make it so they both have the same amount of extra electrons. Keep in mind, protons do not move, just electrons. This is why Ben Franklin was wrong, by the way, because electrons would do all the movement. And so electrons we have to deal with a negative number. If he did protons that did, if he called electrons the positive charge, if that makes any sense, the math would be really easier because that's the stuff that moves. But what happens is when you touch this against it, it'll try to balance out. And when you pull away, that piece will stay negative. Now, if that rod was positive, it would do the same thing. It would just reap more electrons off the sphere, making them both positive. And what happens after you do this? Both objects would have half of the total charge. Now, I'm going to show you this with something called an electroscope. This is all the videos I show, by the way, or most of the videos I show are things that if we were in person, I would have done in person, so I apologize. So what I have here is a rubber rod that I'm rubbing with a piece of rabbit fur. And you can see that there's fur just everywhere. And the thing to the right is the electroscope. It consists of a metal plate and a thin piece of gold foil. When I give this a charge, that charge is going to spread between the gold foil and that metal piece going down. But it's going to be the same charge spread between them. Rubber rod and, trying to remember, it's a rubber rod and rabbit that becomes negatively charged. It's opposite as the silk. And so I have this rod that's negatively charged, and I'm going to take this negatively charged rod, and I'm going to touch it to the thing. Now, when you touch it, you can see this gold foil moved upwards. It went from laying flat to sticking up. And once I pull away, it's still sticking up when I get back to me touching it. The reason why is I deposited some of the charge. That rod was, I want to make sure I'm saying this right. Yep, that rod was negative. Now it's slightly less negative, but inside this guy is a little more negative. It has too many electrons. If I then go and touch it, I'll remove all the excess charge, grounding it, and it'll go back to sitting flat. I think I do it again. I do. Oh no, that's something else. We'll come back to what I'm doing though. Okay. Now I talked about when I touched it, I brought the charge down to 0, right? Like going back right here, jink, it fell back down. And just processing me touching goes from sticking out to, I almost said this badly, sticking out to just going back down we'll go with. You haven't had me long enough for me to start making horrible sentences. The process of me doing that is called grounding. Anytime you connect an object to the earth, you ground it. What it is that the earth is very big. Takeaway lesson for the day, I guess. And it can take a near infinite number of electrons, or it could lose a near infinite number of electrons to have no difference. I mean, think about how small an atom is, and then think about how big the earth is. There's a lot of fucking electrons on the earth. What that means is anytime something is attached to the earth, and by that I mean touching it. In this video, this thing has you can't really tell, but down at the bottom of the ring piece, I don't know if you can actually see my mouse, but it's rubber holding it together, an insulator, so that it only had rubber touching anything else. Me standing there, I didn't have rubber-soled shoes. I was touching the earth. So when I touched it, I grounded it. But anytime you touch something to the earth in some way, or if you have if something plugged in, it's a 3-prong outlet, that third prong, that's a ground. That's going to the earth. But anytime you do that, it'll bring the net charge back to 0. Because if there's any extra electrons, it'll just drop them on the earth. It can take it. If it doesn't have enough electrons, it'll just pull some from the earth. It can change it. See, most things want to have a charge of 0. And so when you try to ground them, they will. Side note, the reason things want to have a net charge of 0 is the whole idea that electrons repel, right? If you have too many electrons, they're all pushing away from each other. So if you have too many electrons, it's going to want to get rid of the extra ones, and so on. If it doesn't have enough electrons, it's going to want more. It's going to be positive charge. So we have negative charge, so it's going to pull in. That's why that happens. To give I don't think practical is the right word. To give a real world example of grounding, I could give practical ones. There's a lot of practical ones, but let's do a more flashy one. This is what lightning is. What lightning is sometimes a cloud can get a charge. The reason clouds get charged is literally clouds rubbing up against each other, just like the silk rod in the thing, that the water vapor can have friction and cause a change in charge. And what happens when there's lightning is that the cloud will have a charge, a net charge, usually negative. Usually the cloud as normally becomes negative. Really, it's a cloud above becomes positive, a cloud below becomes negative, but it's usually the one below is negative. It can happen the other way. It's really rare. What happens is if that net charge is big enough, all the electrons are going to try to push away from each other. It's going to try to ground itself. And if the net charge is big enough, it'll go and try to shoot those extra electrons into the closest thing. Now, the closest thing, often a tree or something like that, but it's, the ground. And that's what lightning is. Lightning is just something due to friction got too much charge, and it's like, shit, I don't want this charge, trying to deposit back down. Sorry, there's a cat behind me and it startled me. Hold on a second. She should not be sharpening her claws on that couch. Okay. 2 minutes. Yeah, I can do this. To show this in a more interesting way, there's a device called a Van de Graaff Generator. What a Van de Graaff Generator is it has a rubber belt that goes over these little teeth. And what happens is by going over the teeth, it's going to rip charge off the belt. And you cause it to spin real fast. And what happens is when it rips the charge, the teeth is kind of attached to an outer bigger dome. And it'll, as it spins, continuously causing this friction, will build up charge on this outer piece. And if you take a second grounded thing and touch it near, you can see the results. Now, we have a Van de Graaff generator at Delhi. And so there it is running. And I'm just going to go and take a grounded piece and bring it near it. And you can see little zaps. And as the zaps happen, and you know what? I'm going to actually do something I don't always do. How do I do that again? I'm going to play the audio for you. Is that as it goes, these little zaps, you can hear them. All that is things trying to ground themselves. A charge coming from friction, and then grounding due to being near an idea. It's the exact same idea as the lightning. Okay? Now, I'm going to stop there because it is 3:49. Quick thing, for those of you who haven't had me before, I do each chapter for a week, but I only lecture for 2 days a week. Here's the setup. On each week, you know what? I'm just going to, seriously? There we go. I did have this prepared before, but as I said, my computer crashed. So how it's going to work is that each chapter is going to be a week long. So for each chapter, I will start it Monday. I will finish it Wednesday. Thursday, there will be a lab on that chapter that's released, due the following Thursday. And Friday will be example problems. Right when class ends each Wednesday, I'm going to post a packet of problems. And then Friday in class, I'll go over them. There'll be the same type of problems on the homework and the exams for practice. So yeah, I started the chapter today. I'll finish it Wednesday. Any questions before I have you guys go?
Nope. I'm all set.
Okay. My cat is attacking my couch more. So I will stop there then. Talk to you Wednesday. Have a good rest of the day.